I'm going to walk you through a guide that explains how to build, train, and use a transformer language model from scratch using PyTorch, based on the famous attention is all you need paper. The tutorial covers everything from data preparation to model definition, training, evaluation, and generation, and it also discusses how to run the code on various GPUs. First, the article starts with a brief introduction. The author, FareedKhan, is looking for a PhD position and has implemented a transformer model from scratch. The code is available on GitHub. Using the provided scripts, you can train a 13 million parameter or even a billion parameter language model on a single GPU. A sample output from a 13 million parameter model is shown, revealing somewhat coherent, but still noisy, text. The highlights of the tutorial are: the training data comes from the pile, an 825 GB open source dataset that pulls together books, articles, websites, and more. The sample code downloads a few small parts of the dataset, extracts text, and builds an HDF5 corpus of tokenids using the GPT-3R50K base tokenizer. The model architecture is a standard transformer with attention heads and multi-layer perceptrons, MLPs. Each block has two residual branches, one for the multi-head attention, and one for the MLP, both preceded by layer norm. The final layer outputs logits over the vocabulary. A series of utility functions and classes are implemented for data loading, training loops, evaluation, and generation. The design encourages reproducibility and easy modification of hyperparameters. Now let's dive into the core concepts and code explained in the article. For clarity, I'll rephrase the key sections into plain spoken language, removing markdown and code notation, while preserving the intent and flow. Getting started. 1. Project structure. The repository follows a straightforward layout. Train-llm-from-scratch SRC models MLP Pi multi-layer perceptron attention Pi single head and multi-head attention transformer block Pi single transformer block. Transformer Pi full transformer model config Pi default hyperparameters data loader Pi data loading utilities scripts train transformer Pi. Training script data download Pi download. The pile data preprocess Pi tokenization and HDF5 conversion. Generate text Pi generation script data storage for raw and process data models with checkpoints are saved requirements.txt Python dependencies. With a repository cloned, you might need to adjust Python path so that Python can import the SRC modules. 2. Installing dependencies. Pip install R requirements.txt. 3. Data preparation. The code uses the pile dataset. The data download script pulls a few shards of the training set and the validation set. After downloading, the preprocessing script tokenizes each JSON line with a GPT-3 tokenizer and stores the resulting integer IDs in a single large HDF5 file. The preprocessing routine reads every compressed JSON line, attaches an end-of-text token, runs encoding through the tokenizer, and writes the flat sequence of token IDs into a resizable dataset. This design allows us to generate random contiguous sequences for training without padding. Model overview. The trainer builds a transformer that operates on integer token IDs. Each token ID maps to a dense vector through an embedding lookup. Position embeddings are added to provide sequential order information. The core of the model is a stack of transformer blocks, each consisting of 1. Layer normalization stabilizes activations. 2. Multi-head attention parallel attention heads capture different relationships. The hidden dimension of each head is the embedding size divided by the number of heads. A causal mask ensures tokens can only attend to themselves and earlier tokens. 3. Residual connections. The block adds its attention output back to the input before feeding into the MLP. 4. MLP with a hidden expansion of feed forward. Network expands the representation by a factor of 4, applies a ReLU activation, and projects back to the embedding size 5. Another residual. The MLP output is added back to the block's input. The transformer ends with a final layer norm and a linear layer that projects each token representation to logits over the vocabulary. If target token IDs are supplied, the model also returns a cross-entropy loss. Data iterator. Training a language model requires sequences of tokens and they're shifted by own targets. The iterator function opens the HDF5 file, determines how many possible sequences fit, and shuffles the indices. It then yields pairs of tensors, the context, input, and the target, the same context shifted one token forward. Each iteration fetches batch-size random sequences of context length plus 1 tokens, slices them appropriately, and moves them to the designated device. Hyperparameters. A configuration dictionary houses all crucial numbers. Vocab size. The total number of distinct tokens, typically 50,304 for GPT-3 tokenizer. Context length, maximum sequence length fed to the model, e.g., 512 for a billion parameter model. N-embed, size of the embedding vector, e.g., 2048. N-head, number of attention heads, e.g., 16. N-blocks, depth of the transformer, e.g., 64 for a billion parameter model. Train path, dev path, HDF5 paths for training and validation data. T batch size, number of sequences per GPU batch, e.g., 32. Learning rate schedule, initial learning rate, decay step, and decay value, number of steps, total training steps, evaluation frequency, and evaluation iterations. The dictionary is passed to all functions that need these values. Training loop, the training script first instantiates the model on the chosen device. It then creates a batch iterator from the training file. A progress bar shows the current loss over a moving window. For each step, 1. Fetch a batch of input and target tensors. 2. Run the model to obtain logits and compute loss. 3. Backpropagate and step the AtomW optimizer. 4. Every few thousand steps, evaluate on a few batches from both the training and validation sets, printing the average loss for each 5. At a specified decay step, reduce the learning rate to a smaller value. The script includes error handling to catch iterator exhaustion and ensures that if an exception is thrown, the partially trained model checkpoint is saved, preventing loss of progress. Evaluation and plotting. After training, the script calculates the final training and validation loss. A typical result for a 2 billion parameter model is a training loss around 0.23 and a validation loss around 0.64. The article also compares loss curves for million parameter versus billion parameter models. The larger model starts with higher loss and fluctuates more before stabilizing, highlighting the need for careful tuning or more data. Text generation. A separate script provides an interface to load a saved checkpoint and generate text. The steps are: 1. Load the checkpoint and rebuild the transformer architecture. 2. Load the same tokenizer used in training. 3. Translate the prompt text into token IDs, appending an end-of-text token. 4. Repeatedly call the model's generation method, feed it a current context, obtain logits for the next token, sample from the probability distribution, and append that token to the sequence. 5. After generating the desired number of tokens, decode the token IDs back into human-readable text using the tokenizer. The article demonstrates generation from both a million parameter and a billion parameter checkpoint using a minimal prompt,